Good afternoon. Welcome to NOAA Central Library's educational platform for the presentation of research and ideas in support of the National Oceanic and Atmospheric Administration's mission. Today's library seminar is titled The Fisheries Integrated Modeling System, a new modular paradigm for fisheries stock assessment software. The presentation is part of the National Stock Assessment Science Seminar Series, which is developed by NOAA Fisheries and organized by Kristen Blackheart. Today's speakers, Dr. Christine Stawitz and Dr. Richard Methot, will be introduced by Kristen. But before I turn the microphone over to Kristen, here are a few housekeeping items for our live audience members to improve your viewing experience. If you have trouble with the audio or visual components of GoToWebinar, we suggest that you log out and rejoin us. This resets the software and usually resolves most technical issues. Our presentation is being recorded and will be available on the NOAA Central Library YouTube channel later today. I've added the link to our channel in the chat box. We are very interested in your questions and we encourage you to ask them throughout the seminar, even though the speakers will not address them until the end of their presentation. All audience members are muted, so type your questions or comments in the chat box under questions, which is located in the control panel of GoToWebinar. So with that last detail, let's get started. The mic's yours, Kristen.
Thank you, Lisa, and thanks everybody for joining us for this special edition of the Stock Assessment Seminar. Just a reminder that we will be back to our normal schedule of the first Thursday of every month with our next seminar scheduled for October 7th. But for right now, it gives me a lot of pleasure to introduce our two speakers for today. I have had the joy of working with both of our speakers for quite a while. We'll start with Rick Methot, who is NOAA's Senior Scientist for Stock Assessments. He has been with the agency for nearly 40 years in a number of roles. And during that time, he's focused on using stock assessment models to inform fishery management and developing national guidelines. Highlight for Rick is receiving the DOC Gold Medal in 2008 for his work developing the stock synthesis assessment model. And then Christine Stawitz will be doing the bulk of the presenting today. And she is a little bit newer to NOAA. Hasn't quite put in her 40 years yet, but she is with the Office of Science and Technology in the National Stock Assessment Program, where she is our FIMS project lead. And that's her primary role, is leading the development of the Fisheries Integrated Modeling System, which is why we are all here today. So without further ado, I will hand it over to Rick and Christine. Thanks for being here to share your work.
Very good. So Christine, could you go ahead to the next slide? I'm going to kick this off with just a brief lead up to FIMS, a bit of my recap of the history that has really made the community ready to do this and our agency ready to do it on behalf of the community. I'm going to start with the World Conference on Assessment Methods, which was held in 2013. It was the result of an ICES NOAA collaboration to deliberate on, how do we advance our stock assessment methods? The community globally had been coming together more and more over the years through the various regional fishery management organizations and participating in reviews of each other's assessments. More and more there was communication happening, and this World Conference really helped bring us together as a body. It was followed by a series of ICES assessment symposium at the annual science conference and similar symposia at American Fisheries Society, and also the World Fisheries Congress, including this week, where there was a very excellent series of presentations just yesterday. At the same time, through this past decade, the CAPM series of workshops grew up. Here's another opportunity where 80 or 90 people would gather together from around the world to deliberate on stock assessment methods. It turned into a great opportunity for us to have experts deliberating on the methods, while students and others were participating and helping to flesh out what it is to have good practices in our methods as we work forward. We captured much of this in the NIMS Stock Assessment Improvement Plan in 2018. And here we really saw that it was beginning to be time to be thinking about how do we go about building a next generation platform in order for us to conduct our stock assessments. The CAPM workshop in 2019 was the first that was a significant international collaboration. Here it was held in Wellington, New Zealand, and co-hosted with New Zealand. And it really pulled together the experts again to talk about what are the essential features needed for the next generation of model. The paper by Punt et al. In 2020 really captured the results from that workshop, and a link to that paper is found at the end of your presentation that you've been able to download. Through 2020, the NIMS Science Board deliberated on what's the state of this, what's our readiness, are we ready to move forward with this? And nearly a year ago, we arrived at the conclusion that we were ready, that we had the resources, we had the commitment to move forward, and we were able to launch the FIMS project at the end of 2020. And through this year, we've been kicking it off, hired Christine, got the project started, and I'm going to turn it over to Christine now to have her tell us about it, where we're at now, and where we're looking to go. Thank you.
Okay, thanks, Rick. So I'll give a very high-level overview of FIMS first, and then go more into detail of the parts of FIMS throughout the rest of the talk. So some of you here may be wondering what it is. This might be the first time you're hearing about it. We envision FIMS to be a suite of tools. Actually, I think, Rick, have you muted yourself? There's someone not on mute. I'm hearing in the background. Thanks. A suite of tools, primarily for stock assessment, but with more linkages and more pieces that connect to partner disciplines like ecosystem, climate, and economic models and data. The thing I'm going to say over and over again that I really want you to take away from this talk is its flexibility, and flexibility in a way that thinks about future developments in fisheries modeling, not just where we are today. And the other piece I think is the most important is everyone here today, the community. This is an effort that spans many, many people beyond Rick and Kristen, and goes to every center as well as across a number of academic and international partnerships. And it's really key, I think, that we all collaborate to make this a success. And if we do that, I think we can address numerous priorities for NOAA going forward with fishery stock assessment modeling. The first part of why FIMS seem to be needed is that we are moving more and more towards a more integrative modeling approach for fisheries assessments. As many of us probably focus on this middle cog in the wheel of fish species population dynamics, but we know that we have partner disciplines with models that have huge implications on fish populations in the natural world, the climate and ecosystem they live in, as well as the human dimensions of fisheries and other anthropogenic pressures on fishes. So we really need a way to bring these together in a way that is hard to do right now. Another main motivation for developing FIMS is that a lot of our existing suite of models come from kind of a research background, which makes sense. Most of us are researchers, but it means that the development of these models is kind of focused on research and not as much in production or long-term use and long-term maintenance. Many of the existing models have had a lot of new features added and a lot of customization, but it tends to be difficult to reverse engineer these customizations in. There's difficulty in maintenance. A lot of these models are different to separate out into their respective pieces. or they have kind of one key person or a couple people who are responsible for their support in addition to some other day job that they have on top of model maintenance. Finally, a lot of the existing software is built on platforms that are not up to scale with the newest advances in computing, like cloud computing and new speed ups in programming and computational abilities. Next, I want to introduce the group of folks collaborating on this, many of whom are here today and should be recognized for their role in this presentation as well, and I'll get to the individual names next. We've got a big community spanning NOAA Fisheries and external. Within Fisheries, there is collaboration from the leadership that has provided oversight and align us with national priorities. Our team on the Office of Science and Technology that's responsible for the key software engineering. The representatives from each science centers on our implementation team that are co-developers of the model and kind of representatives at regional offices, subject matter experts in partner disciplines like ecosystem and socioeconomics. And then we've got another group that we want to be listening to on their individual comments and review of the model, and external counsel, and the open science community of users of stock assessment software. The implementation team is going to be doing the bulk of the development and testing and rollout of this model and has already been meeting for several months. So on the left-hand side, you have here all the representatives from OST, as well as contractors for ECS Federal supporting S&T. And then on the right are regional experts in stock assessment who are collaborating to help design and develop this software. We just established a FIMS council that consists of representatives from academia, fishery management councils, science and statistical committees, international management bodies like ICES and CSIRO, and developers who work for other agencies or on other similar next generation projects at NOAA and JRC, as well as representatives, again, of ecosystem economic modeling. We also really want to collaborate and complement a number of synergistic efforts going on across greater NOAA and NOAA Fisheries. Some of the ones in NOAA Fisheries that are most close are the Climate Fisheries Initiative, the Ecosystem Modeling Strategy, and High EBFM. Rick mentioned SAIP implementation. These are all partnerships that we need to work with and complement in terms of achieving the same goals, which is expanding the suite of our models to be more comprehensive. And then from greater NOAA, we can learn a lot from other modelers in the weather side or the climate side who've already really done a lot of work to create these partnerships across academia and really large scale coding efforts on GitHub for things like the GFDL climate model. So here's that same group of people in a schematic. So in the center is the implementation team. Again, these are the folks that are doing the bulk of the actual coding and testing. But we have a lot of coordination and communication across many groups between the external FIMS Council, other modeling communities, the science board, and the users and testers of the software. And so the goal here is really to distribute the knowledge and the expertise of the system so that we don't have a single point of expertise or failure, so that we have more support built into the model structure from the beginning. Okay, so that was the introduction. Now I'll go into how we've been planning FIMS, the timeline, and the requirements. If you've been involved in computer programming for a while, you've probably seen or heard of the software development lifecycle. And I know many people here are more fisheries scientists, so I'll describe it if you're not familiar with it. There are many different paradigms of the software development lifecycle. I think the key thing that I think is one of the most important components of the software development lifecycle, which is illustrated on this circle on the left here, is that development, we tend to think of development as kind of the main part of the model process, but it's really just one step in a larger cycle. So before you ever write any code, there are these three phases: planning, analysis, and design, in which you outline what you're going to do and why, and prioritize and plan before you even start the development. And then the development phase is, of course, the one that we may be most familiar with as model developers. But there's also this testing and integration and maintenance piece, and we need to plan for these pieces to happen before we start implementing as well. I'm going to mention requirements a couple times, so I'll just define requirements loosely as the suite of capabilities that the users expect or need from the software. These don't necessarily have to be explicit, they can be implicit. They span things like functional requirements, which are actually functionality, and non-functional requirements like ease of use and speed and security. So we are developing the requirements as an important part of the planning and analysis phase, which precedes the implementation. The other really important aspect of the software development lifecycle is that it's iterative. And so this iteration allows for testing and incremental expansion of the software, which increases stability and reliability and results in production level software beyond what you might see for more of a research single use model. And even though our goal is to create production level software, the whole time we really want to have a clear pathway for how we're going to integrate future research and development into this production branch. And so if you or a grad student has a research project, we want you to be able to take this software, create a fork or a branch on GitHub, test out your new feature there, and then go through some kind of approval process where we can check it back into the production level software if we find, this is a stock assessment best practice, we should do it, rather than having folks need to start from scratch when they're building up new assessment model features. Okay, so that was the general software development lifecycle. Here I've adapted it, just these 6 stages, to FIMS. Right now, I would say our group is here. We are at the beginning of the design phase. For the last 6 months, we've been focused on assembling the team, eliciting requirements, and then prioritizing them, and outlining the sections of the implementation plan. For the next several months, our focus is going to be writing the implementation plan, which we'll then review with the community that I've described in previous slides. In the first half of 2022, we'll start development milestone 1. And this development milestone 1, because this is an iterative process, we're really trying to get to what in software is usually called a minimum viable product, which means we're not going to have a model that can fit every fishery. It will be software that kind of satisfies the minimum expectations of a stock assessment model so that we can start doing some more advanced testing and beta rollouts. In the second half of 2022, we really want to take time to test and integrate what we've made. So we want to run both unit tests of individual components of the system and integrated tests of whole population models. And if possible, have folks from other science centers test this out on kind of their poster poster fisheries, the types of fisheries that don't have inherent complexity or poor data, but to make sure that we, from the beginning, are finding the gaps of where the software is now and where the science centers need it to be to move into a production environment of the tactical assessment. The requirements gathering process was something our implementation team participated in the spring and summer. So each of our center reps, as well as our subject matter experts, went off and brainstormed a list of, I think we ended up with 287 requirements, which are categorized by area as well as by given a priority for future accuracy, as well as how much it's needed to meet current needs of assessment scientists. And here we covered both, as I mentioned, the functional and non-functional requirements, things that we need the software to do, but also non-functional requirements like, I think you'll see on here, ease of use or usability is another part of this. One thing I want you to take away from this very noisy word cloud, which was just a way of visualizing 287 requirements, that's a lot of text, is that we don't just want to replicate existing functionality, but we really tried to be forward thinking of what an ideal system would do. And so you can see things in here quite large, like movement and predator prey, that an existing suite of assessment software might not do as well, but we know that it's going to be important going forward, as well as all of the needs for things that are done today. Recently, we've divided into focus groups that will comprise the sections of the implementation plan that we're starting to write. The 5 focus groups we've identified are focused around software platform. This is the actual language and terminology that we're using to write the software. Software architecture, which is more about the structure and the separation of different model components and how they interact with each other. Files and input and output, developing a testing plan, and coming up with our workflow that we're going to use to coordinate development across this big group, making sure that we are effectively collaborating and not overwriting each other's changes. The 2 that kind of seem the most important to hammer out first are the software platform and software architecture considerations, and that's most of what I'm going to talk about for the rest of the talk. The software platform investigation was led by Andrea Havron, our contractor with ECS Federal, and the following slides are her slides, so I wanted to give her credit there. We really wanted to be mindful or thoughtful about which model building environment and which software language we wrote FIMS in. We didn't want to default to the language that we might be the most comfortable with or that we have the most experience in. We really wanted to evaluate which was the best for the requirements we identified. And Andrea looked into this from 2 aspects. One was familiarity and knowledge, and one was the ability of the software to meet our requirements. So we did a quick survey of the implementation team and their preferred model building environment for a complex nonlinear population model. For each of these graphs, the scales are on the bottom or the x-axis. 0 represents participants who had no experience with this model building environment. 1 is basic, meaning you've used it, but struggle to get very far without assistance. 2 is intermediate, you can use it okay, but you're not an expert. And 3 is advanced, the type of power users we expect to not only use the software, but be able to contribute to writing the software or debugging extensively under the hood of the model. So we surveyed about a number of different platforms and languages and found, unsurprisingly, probably to this community, the most commonly preferred model building environments are ADMB and TMB, with slightly more advanced ADMB users in the group than TMB, but pretty close. A lot of our participants had some familiarity with C++, but didn't feel like they could list themselves as intermediate or advanced. And then we had a couple of intermediate and advanced C++ developers. And RCPP was even less, with only 8 participants saying that they had used RCPP, which is the R interface to C++ modules and software. Next, Andrea took a number of our requirements. So here on the left, I just have a couple of the structural requirements that we identified. And she looked at how well each of the modeling platforms did to meet the needs of these requirements. So squares that are in gray represent platforms that can meet that requirement on the left. White is ones that cannot. And NA are ones for which it's not applicable. So here you'll see, in addition to ADMB, TMB, C++, and RCPP that we had previously, there's also Julia and Stan. We really did look pretty broadly at all the different platforms that are out there, although I think, as you can see here, Julia really doesn't have a lot of the capabilities to meet our requirements, which is why it's probably not something we're going to move forward with. And Stan has been difficult to adapt and customize, but we did look at them as well. So as you can see here, really ADMB and TMB are coming out as the ones that more meet our requirements, with TMB having the added benefit of not having the additional TPL to CPP customization step, which is why it scored higher than ADMB on portability, since the code could be more portable. C++ and RCPP, because their languages and interfaces often just didn't really fit into this requirements categorization, but did in for some of the requirements. Okay, next I'll talk about the software architecture. This is a complex diagram outlining the vision of FIMS architecture that we have in mind. I'm going to go through each of these sections of the architecture in subsequent slides, so fear not, I will break it down in smaller pieces. What I think I want to show in this big diagram is the difference in color coding of the different boxes. So things that are this light blue that matches the background of this image refer to pieces of output or input into the system. Dark blue refers to software that we will either write or import from other places. And this kind of medium teal is an interface. And by interface here, I mean more like an application programmatic interface or API, not necessarily like a graphical interface. And these pieces are basically translators and publishing layers that make different pieces of the model accessible to each other, as well as sometimes published externally. What I see as the building block, or maybe even the foundation is an appropriate metaphor for FIMS, is a base math library. And this, I think it's very important that this consists of a series of separate and exported functions that can be reused in other places and are documented and exposed properly in the interface. This refers to both key mathematical functions like, statistical distributions. And for those that are kind of more standard mathematics, I think we should look at existing libraries in C++ that have a lot of this functionality already developed. We're not necessarily going to reinvent the wheel. We'll import other functions where possible. But I think this should also include standard fisheries equations, like a Beverton-Holt recruitment function, for example, that, even if you're not going to run a full FIMS model, you can call that Beverton-Holt function through this RCPP interface. And I should say this isn't kind of the first time this sort of system has been proposed. It's sort of the vision of things like Gadget and other more fisheries toolbox type efforts that have been going on. The other key piece I see here is that you can call these functions either from C++ or R, or perhaps from TMB, since it's just a C++ function, which will allow for things to be portable between other tools like management strategy evaluations, ecosystem models, and other stock assessment tools that might not be part of the FIMS system. Separating this outside of the modeling layer, which might be how some of us have been used to writing it, makes it easier to do unit tests. So we can confirm, hey, if there's a problem in the model, we know that it's not in the, recruitment or selectivity function, because we've already run a unit test on that and it's passing, and we have an automated process for testing that. And we don't have to run a full population model and then debug the pieces. So those are the parts. That's another reason why I think this is so key to keep separate and modular. On the right-hand side here is a data processing library. And this is the interim step of going from the raw data to a form that can be read by the FIMS system. This is something that came out maybe most overwhelmingly from our requirements gathering process, was that stock assessment analysts spend a ton of time pre-processing their data. Some of that pre-processing is standardized thanks to things like Kelly Johnson's West Coast package, but other times the data processing is entirely custom for each assessment model or for each region. And it takes up a ton of time and is often not well stored or stored in a reproducible place. And so we really want to build up a reusable library of pre-processing functions for all of the different data types that go into stock assessments. And this is complex because it varies by region and it varies by data source, how this data are processed. But we need to document and reproduce that in this library. There are a couple of, so again, separating it allows it to be region specific. It allows us to test and call these data processing functions independently or as part of the workflow. And it enables us to easily add new data types because we know more data types are always becoming available. Finally, and one of my favorite things about this, if we can do it well, is that it will allow folks to check the data visually prior to entering it into the model. So there's been some other efforts where there's more automated processing and visualization of data so that right away when it enters the database or you pull it out of the database, you can say, hey, there's, this data point is a total outlier. Why is that? Before wondering why it's affecting your model. And this is a best practice, but it's something that can be hard to have time to do manually when you're in the throes of an assessment cycle. And so automating that with a set of standard checking and visualization tools, I think is going to be really beneficial. In the middle here is the modeling layer. This is what I think many of us would often think of as the canonical part of the fisheries assessment model, where you loop through the population, build up the objective function and likelihood, etc. I call this a layer and not a model because in my mind, we really want this to be multiple models. We don't want to gum up a data limited or data moderate assessment with a lot of computation that isn't needed. And so we can create different components of this model for different structures of the population or different levels of complexity. And this will again separate out the pieces into more manageable chunks for testing and again, reducing complexity if you don't need it. This has the additional benefit that it'll be easier to compare between different types of models. Everything will come out of the data processing library in compatible formats. And so it'll be easier to compare a simpler model to a more complex one, to do more model validation like likelihood ratio tests before we expand complexity. And it'll also allow us to more easily do model averaging or ensembles because we can compare between different structured models more easily. So what I've just described, I think, would be called a modular tiered architecture in computer science world. And it's a really key part of software engineering. And I think for fisheries stock assessment software specifically, it'll support our goals, even if we never want to advance our models, even if we just want to do what we do today better. It will allow us to start with simpler models and then reuse the components of that model elsewhere, like management strategy evaluations. It'll allow our community of developers to only touch small pieces of the model, reducing the potential for merge conflicts. It'll allow us to more easily span from data limited to data, high data, rich data systems, and do more comparative model building where you start with a simple model and compare it to a more advanced model. This will also give us the flexibility to change in the future to certain things we already kind of know we should be doing but aren't doing in operational models yet, like more ecosystem integration and incorporation of socioeconomic processes. There are also types of data that are being collected, like electronic monitoring and close-kin mark recapture, that we can incorporate better through things like the data processing library. And we're not gonna pretend to be omniscient. We know that there are gonna be developments in the next 10 or 20 years that we'll need flexibility to grow with. And we can't anticipate those, but we can at least build something that's more scalable because we know they're coming. I'll just close by talking through kind of an example of a next generation feature that FIMS can support. It's been a very clear mandate that we need to do a better job of adapting to and planning for climate change in our fisheries management models. And we know that climate is not the only type of variability that fish populations experience. There's lots of spatial variability. There's temporal non-climate variability. There's anthropogenic influences, multiple species dynamics, and then observation error, because we never sample or observe the ocean perfectly. And we know from the statistical literature that if you want to partition some data into different sources of variability, that random effects models are a best practice to do so. When we think about how we understand this variability, random effects really help us integrate out population level variability, like spatial variability that affects our population. And it's really important that we integrate out those sources of variability before trying to integrate external population drivers, because it makes us that much more confident that our drivers are actually what is driving the population. And here I have an example of this from Tim Miller's 2016 paper, Modeling Climate Influences on Yellowtail Flounder. And here he found that the cold pool index did affect yellowtail flounder. However, it was important to understand that the cold pool was not perfectly observed in this system. So by capturing the observation error in this process of the cold pool index was really important to understand the actual magnitude of the index on the population. And I think this is one example of how we need to account for all these different sources of variability as we move forward to making our models more integrated. We can't forget about randomness and things that we don't observe. Random effects models also improve our inference. So right now, a lot of our models use a penalized likelihood approach. In the statistical literature, we've shown that true maximum likelihood estimators would be more consistent, but with penalized likelihood, we don't have those, and it leads to unreliable estimates for model comparison, selection, and weighting approaches, many of which use some function of the likelihood. But random effects have the benefit, as Jim Thorson wrote in his 2019 paper, you get a more consistent estimate of recruitment variability. There's more straightforwardness and bias adjustment. And instead of complex data weighting schemes, you can handle over dispersion as random effects added to compositional data. And going back to the previous slide, there is hierarchical variance structure in our data. We know that there is variance from climate, but that it's mediated by the variance that we observe spatially. And these sorts of structures allow us to handle that hierarchical variance more smoothly. So I'm just going to close and hopefully leave a lot of time for questions. FIMS is really a bridge from where we are today to the next generation models we need to use. Developing the system will allow us to incorporate best practices for capturing these many types of variability, separating out modules and incorporating a lot of interface flexibility so that folks can call it from different programming languages will help us reuse parts of this model across partner disciplines, as well as make the research to operations or to production pipeline more smooth. And we're going through this very systematic planning process to ensure that we can scale from where we are today to where we need to go. So what we see as the key benefits of this is that it moves us towards a more integrated and interdisciplinary approach via flexibility and scalability from simple to complex. That it, through this modular interface, can be more integrated and connect components of different models. And again, it all comes back to the community. This is not something we're doing alone. We're working with across centers, with international partners, and with other modeling efforts at NOAA to ensure that we're doing this right. So with that, I will just throw up the references, which you should have in the handout if you want to look at any of these papers in more detail. And I will take any questions or comments. Thank you.
Thank you, Christine, and Rick as well. We have lots of time for questions, everybody, so I encourage you to ask them. You can do that by entering them in the questions chat box, which is in the GoToWebinar control panel on the right side. Also, I just want to mention before I start asking or reading the questions out loud, that Christine and Rick have shared their slides. Christine mentioned that, and it has all this wonderful material. So if you're interested, please go ahead and download them from the handouts area, again, from the control panel on the right side. So we do have a question, and this first person asks, could you speak to the staffing forecast for how or who we anticipate long-term maintenance of FIMS? Does NOAA intend to support a core team of developers, federal/contractors, for the next X years?
Yeah, there is, as I mentioned, there's a number of us on OST who are, this is one of our core functions that we were hired for. So yes, there's us. And there's also commitment from each of the science centers to provide staffing, largely because, you know, this is an effort that is done for the purposes of regional assessment scientists, and it should save regional assessment scientists a lot of time. So we're trying to not necessarily, we're trying to get all the assessment scientists working in the same direction and working together through this allocation of each regional center to this effort.
Thank you. This next question asks, how has the fisheries community responded to the idea of next generation modeling becoming a component of stock assessments?
Well, from, as Rick mentioned, the World Fisheries Congress is going on this week, and from the reception we had last night, it seemed like there is a lot of interest in next generation assessments. Another really important piece that came up that I think we shouldn't lose sight of is that, you know, it's all well and good for data-rich species to continue to go in these more and more complex directions, but we can't forget that a lot of fisheries in the world are data limited and not necessarily able to do a lot of this complex stuff, which is why I think we really need to make sure that this scales down to the data limited case and not forget about data limited and data poor species as we're developing this system.
Excellent. Next question says, thank you, Christine. I was wondering about the math library. What kinds of math algorithms are going to be in it, and how much is going to be developed by the FIMS team versus taken from existing libraries?
Yeah, great question. I think it depends on which, I think we have a pretty clear idea of the software platform direction we're going in, but it is a little bit dependent on that in terms of whether the systems we're using are a static or a dynamic computational graph. And if it's a static computational graph, then we need to rewrite any function that doesn't have an atomic function already surfaced through a different interface. So an example of this would be like the Cholesky decomposition is really key to quick estimation of random effects in a Laplace approximation. And so if we were to use something like Template Model Builder, that already has an implementation of the Cholesky decomposition. But if we were to use kind of bespoke C++, we might have to reuse or rewrite that ourselves, depending on what type of automatic differentiation we were using. I think that there is I'm not gonna pretend that we've fully gone down this rabbit hole, but we will. There's a lot that's already been implemented in, whether it's in Armadillo, which has a lot of matrix operations or matrix algebra already written, or things like TensorFlow that have a lot of this math library already done. And so I think if we really want to move quickly, we need to stop reinventing the wheel and writing a lot of things that are kind of standard solving algorithms from scratch, reuse the ones that are already there. And then I think for the fisheries specific or ecological specific functions, that applies as well, where if there's something that's surfaced through FLR, another of these existing fisheries toolbox efforts, we should try to reuse it where we can. And we might only have to write things that are more emerging research, like the Dirichlet multinomial approach to handling composition data, things that are more specific. I think we will have to write from scratch. But I do think I kind of was really influenced by Sarah H's comment at the multi-species modeling workshop for this math library. It really shouldn't be a specific to FIMS library. It should be something that can be used by ecosystem modelers as well. Yeah, so I really think it should be reused across not just stock assessment approaches.
Excellent. We do have another question. This question asks, how can you be sure that the underlying architecture, will allow the inclusion of a specific feature in the future, for example, CKMR?
Yeah, I think the important part of this is the flexibility and the iteration. So, we can never be fully sure before a thing happens that we will be able to account for it. But the key is to build in enough flexibility into the system that we can be reactive to new developments. So we're going to learn as we go. And this first iteration, we could write the system, in a way that we later think, that actually wasn't that wasn't the most efficient way to write the system given this new development. So we'll have to change some things, and change is a natural part of any software development process. I think the key piece here is that we will have a community of people, and we will have a training program on this system, and we will have, there will always be capacity to adapt to new changes, and how things are currently done will be better documented and tested. So there'll be capacity to adapt to new changes because there will be, other developers who may be more familiar with something new like CKMR, who are trained on this system rather than it having to be kind of an afterthought that's added into a system that was designed for something very specific. So yeah, I can't say we can guarantee that every new feature is going to be ready, but it's more that we are adaptive and building the system in a way that isn't thinking it's going to be static forever.
Okay, this next entry here is more of a comment, and it says, the suggestion that random effects model formulations are a panacea for partitioning sources of variability, or in effect the error structure of a model or ensemble model, is an assertion that needs further technical support, especially for nonlinear time series models with heterogeneous or field data and multiple working hypotheses about how the fishery system works. Any comments?
Yeah, I certainly don't think random effects are a panacea, and there's only so much you can model. If you don't have the data, no amount of random effects inclusion or state space modeling is going to model your way out of that, as I've found when trying to fit random effect state space models to growth data. So there are, of course, limitations. And I think that's why the other part of this that I think is really important is the scalability from simple to complex. And, we really need to always have a simpler iteration of the model to do, a likelihood ratio test against and say, hey, does this feature that we're adding, do we actually have the data power to support addition of this new random effect or this new component of the model? Or is it just our data are what they are, and that means we're going to have to simplify things? So I think that the random effects and the ability to scale down the model go hand in hand, because you always need to be testing whether that random effects variance actually is supported by the data, or if it's just estimated at 0, then that random effect isn't going to fix anything.
Excellent. We do have lots of good questions here. This next one that you or Rick can answer asks, the assumption of uniformity over space is one of the most problematic in stock assessment. Is FIMS going to address this?
Rick, do you feel like answering one? I want to give you a chance to answer some questions too.
Sure. I'll just step in here. And, certainly having a readily accessible spatial capability is something that is high on the wish list for the assessment community. There are models that do multi-areas. There's actually a test underway across several of those models happening in this coming year, and we're involved with that. And so we're very interested in having more spatial capability. And we also see that there's other developments that are happening at a much finer spatial scale that's moving in a direction that is meeting us hopefully midway. Some of the Gaussian field approaches to fitting a non-parametric surface to the observations that we have, and now putting dynamics onto that. So now you have essentially hundreds of points that are moving across time in a way that has some dynamics to it. That's another whole area of model development that we will be, we're certainly aware of. Certainly, we have people in NIMS working on that, and it's looking at spatial modeling from a highly dimensional approach rather than the working from multi-units stock approach, and adding on some areas is the approach that we probably start with FIMS, but we certainly are aware of the full spectrum of spatial capabilities that we need, especially as we look to link up with more habitat information, more climate information, which has its own spatial granularity to it. And so, it's certainly a high topic for us to be attending to.
Thank you. This next question asks, once there is a working program, what do you envision being the time frame for adding a new module/function to the program? Will there be flexibility to add in a module or function without being first approved by the FIMS team?
Yeah, I would say definitely it's hard to predict the future, but my guess would be yes, you would be able to add your own module without getting our consent or agreement. Just because of the NOAA GitHub policy, we can't incorporate changes into the working operational branch of FIMS from non-NOAA collaborators. And so one of us would have to be testing and approving those changes before they go into the production branch. But I think that will be a mark of, I think I've explicitly written that as a criteria for success, that individual authors will feel comfortable forking the code, writing their own module and testing it. I think that will be success.
Yeah, let me just add that, if we're going to move forward together on this, we need to get the whole community comfortable with the idea of, yes, having a fork of the code and trying something out in research mode, maybe even doing an assessment with your fork of it, but to be open to working with us as a community to move into the main code, something that we all agree is going to work well and is something that we want to make accessible to the whole community. There are other models that are working in this direction, other NOAA models that work in that way. So we essentially have a research branch side by side with the operational branch. So we certainly will support both of those approaches, and having a good research to operations pathway is what we envision on this. But it's going to take some discipline in order to get accustomed to working in that mode. And I hope that we could find ways to get to that place.
We have two more questions and we're getting close to the end of the hour, but this next question asks, has there been consideration of routinely storing the output of FIMS assessments in a unified and efficient format in central repository within the FIMS platform? For example, using similar principles as the Fisheries Library, FLR, or stockassessment.org in Europe?
Yes, in fact, we just met with Arnie Magnuson like 2 weeks ago to talk about the TAF, Transparent Assessment Framework, and how they do that. I think there are a lot of privacy concerns that we have to address if we talk about storing assessment models and outputs in a repository. And we haven't fully worked through all of those concerns, but I think we have a pretty clear idea that this is a need that we need to address, and it's on our radar, and we've talked about it. Yeah.
Yeah, let me just add that, you know, from the perspective of the stock synthesis model, we get asked many times, can we see all of the models that are being used? And we can't do that. We don't know. And people who want to do a meta-analysis across all the feature usage, we can't do that because we don't have the information. So I see it as a very high goal for the community to be able to find ways so that we can be sharing things more collaboratively along those lines, while recognizing, you know, that some of the data that goes into an assessment is confidential, and there are, you know, potentially some privacy concerns. Nevertheless, you know, for our assessments, you know, they are open, and you know, we need to you know, find ways to make best use of it for the research side of things.
Excellent. So here's our very last question for the day. It asks, modularity is great, but sometimes performance comes from tight integration that can conflict with modularity. Have you thought about this conflict and how to solve it?
Yes. I don't think we have a solution yet. It's a good point. And I think, like, that's why part of the architecture, I think, is that I think we need to do a better job separating out different levels of complexity of the model, so that it's not all just one big executable. And we've also been working on, I think it's not really a natural function for most fisheries scientists to think about software performance, but we've started building capacity within the team of running via Andrea's software platform investigation. You know, she's getting really up to speed on how to run performance tests, and working with Matthew Supernar, our software architect, on how to do that. And so I think that benchmarking and performance is going to be a big part of testing and development. But yeah, before the actual development starts, I'm not exactly sure how to balance those needs.
Well, thank you both for answering all these great questions, and thank you to the audience for asking them. I want to encourage everyone to share the recording of this webinar with interested colleagues. I'm going to upload it to the NOAA Central Library YouTube channel in a couple of hours, and I think it's a wonderful resource to share. Thank you both for this fabulous presentation. I also want to just let you know that there were some questions that were not addressed, so if you did ask a question late in the game, we will be sending them to Christine and Rick after we go offline. Again, audience, I'm glad you joined us for today's library seminar. NOAA Central Library is very proud to present the work of the NOAA community and its partners, and we hope you'll join us again for a National Stock Assessment Science webinar, which we host every first Thursday of the month at 3 p.m. Eastern Standard Time. And as Kristen mentioned earlier, the next webinar will be on October 7th. Just go to library.seminars@noaa.gov to register. So enjoy the rest of your day, and thank you for joining us today. Take care.